Ever pondered the difference between an adjacency list and an adjacency matrix? It's all about how we represent connections in a graph. In the world of computer science, graphs are a pivotal data structure used to represent networks, relationships, or any scenario where things are interlinked. But how do we express these links? That's where the adjacency list and the adjacency matrix come in. Let's start with an adjacency list. Picture a graph in your mind with vertices or nodes and edges that connect these nodes. In an adjacency list representation, each node gets its own list, filled up with the nodes it's directly connected to. So if we have a node A connected to nodes B and C, the list for A would contain B and C. You can imagine this as a social network where each person's list contains their friends. Moving on to the adjacency matrix, this takes a slightly different approach. Instead of lists, we use a two-dimensional array, a grid if you will. The rows and columns of this grid represent the nodes of our graph. If two nodes are connected, we place a 1 at the intersection of their row and column. If they're not, we put a 0. So our social network becomes a party guest list, with a 1 if a person knows another, and a 0 if they are strangers. Now, you might wonder, which one is better? Well, like many things in life, it depends. If you have a graph with few edges, an adjacency list might be your best bet. However, if your graph is pretty dense with many edges, or if you need to frequently check if an edge exists, an adjacency matrix could be more efficient. But that's just scratching the surface. Both these concepts have their own intricacies, strengths and weaknesses, and understanding these can help you make an informed choice when it comes to representing graphs. So, ready to dive deep into these concepts? Brace yourself. First up, let's unravel the mystery of the adjacency list. An adjacency list is a common method for representing a graph structure. It's a way of showing which vertices, or nodes, are connected to one another. Essentially, it's a list of lists, where each vertex in the graph has its own list that identifies its neighboring vertices. Imagine a group of friends at a party. The adjacency list would be like a list of each person at the party, and who they're friends with. If Alice is friends with Bob and Charlie, then Alice's list would include Bob and Charlie. Now, how do we implement this concept in a more technical setting? We use an array of lists. Each element in the array represents a vertex, and the list associated with each vertex contains its adjacent vertices. Let's take a concrete example. Suppose we have a graph with 5 vertices, numbered 0 to 4. Vertex 0 is connected to vertices 1 and 3, so its adjacency list is 0 to 1, 3. Vertex 1 is connected to vertices 0, 2, and 4, so its list is 1 to 0, 2, 4. And so on for each vertex. This representation is particularly useful for graphs with a lot of vertices, but not so many edges, which we call sparse graphs. It's efficient in terms of space, as it requires only as much space as the number of vertices plus the number of edges. Moreover, the adjacency list makes it easy to find all the vertices adjacent to a particular vertex. You just need to access the list associated with that vertex. This makes it a handy tool for many graph algorithms that require you to traverse the graph, like depth-first search or breadth-first search. So that's the adjacency list for you. A simple yet effective way to represent connections in a graph. Now that we understand the adjacency list, it's time to explore its counterpart, the adjacency matrix. The adjacency matrix is another popular way to represent the connectivity between vertices in a graph. Unlike the adjacency list, it uses a two-dimensional array where the rows and columns correspond to the vertices of the graph. Let's visualize this. Imagine a grid, with each cell representing a connection between two vertices. The value at a particular cell, say matrix, indicates the presence or absence of an edge between vertices I and j. In the case of unweighted graphs, the value is typically 0, meaning there's no edge, or 1, signifying the existence of an edge. However, for weighted graphs, the value can represent the weight of the edge, providing us with more detailed information about the relationship between the vertices. Let's take an example to illustrate this. Consider a simple graph with 4 vertices, 0 through 3, where 0 is connected to 1 and 3, 1 is connected to 2, and 2 is connected to 3. The adjacency matrix for this graph would look something like this. For vertex 0, it would be 1, 1, 0, 1. For vertex 1, it would be 1, 0, 1, 0. For vertex 2, it would be 0, 1, 0, 1. And for vertex 3, it would be 1, 0, 1, 0. This matrix effectively captures the connections between all vertices in our graph. Implementing an adjacency matrix is straightforward. We create a two-dimensional array of size n x n, where n is the number of vertices in the graph. Each cell in the array represents a potential connection between two vertices. If an edge exists between the vertices, we mark the corresponding cell with a 1, if not, we mark it with a 0. And there you have it, the adjacency matrix, a different approach to graph representation, but no less useful. It offers direct access to the relationships between vertices and is particularly effective when dealing with dense graphs or when frequent edge existence checks are necessary. However, it may require more space than an adjacency list, especially for sparse graphs. So as always, the choice between an adjacency list and an adjacency matrix will depend on the specific requirements of your problem. Now let's put the adjacency list and the adjacency matrix side by side and see how they compare. Looking at the space complexity, the adjacency list requires space proportional to the number of vertices plus the number of edges. In contrast, the adjacency matrix demands space proportional to the square of the number of vertices. Simply put, for larger graphs with fewer connections, the adjacency list is more space efficient. When it comes to checking the existence of an edge between two vertices, the adjacency list requires us to traverse the list of one of the vertices, which can be time-consuming. On the other hand, the adjacency matrix allows for this check in constant time by accessing the corresponding entry in the matrix. So if your task involves frequent edge existence checks, the adjacency matrix might be your go-to choice. Next, let's talk about traversal efficiency. Traversing the adjacency list of a vertex allows for efficient exploration of its neighbors. However, if you're using an adjacency matrix, you'll have to traverse all vertices and check the corresponding entries in the matrix, which can be a bit less efficient. Finally, let's consider insertion and deletion of edges. With an adjacency list, these operations can be quite efficient, especially for sparse graphs. But with an adjacency matrix, insertion and deletion can be less efficient, particularly for dense graphs, as it may require updating many entries in the matrix. In summary, adjacency lists are great for sparse graphs with few edges and when insertion or deletion operations are frequent. Adjacency matrices, however, shine when dealing with dense graphs with many edges or when frequent edge existence checks are required. As you can see, both the adjacency list and the adjacency matrix have their strengths and weaknesses. It's all about choosing the right tool for the job. Well, we've covered quite a bit of ground today, haven't we? As we reach the end of our journey, let's take a moment to revisit what we've learned about adjacency list and adjacency matrix. We began by defining these two concepts. An adjacency list is a representation of a graph where each vertex is associated with a list of its neighboring vertices. This can be implemented using an array of lists, with each element in the array representing a vertex, and the list associated with each vertex containing its adjacent vertices. On the other hand, an adjacency matrix is a two-dimensional array used to represent the connections between vertices. The value at matrix signifies the presence or absence of an edge between vertices I and j. When it comes to their implementation, the adjacency list requires space proportional to the number of vertices plus the number of edges, while the adjacency matrix requires space proportional to the square of the number of vertices. Checking the existence of an edge between two vertices can be done in constant time with an adjacency matrix by accessing the corresponding entry in the matrix. However, with an adjacency list, it requires traversing the list of one of the vertices. Traversal efficiency also varies. Traversing the adjacency list of a vertex allows for efficient traversal of its neighbors, while traversing all vertices and checking the corresponding entries in the matrix can be less efficient. When considering insertion and deletion of edges, the adjacency list can be efficient, especially for sparse graphs. However, insertion and deletion of edges in an adjacency matrix can be less efficient, especially for dense graphs, as it may require updating many entries in the matrix. So, whether you're dealing with a sparse graph or a dense one, you now know which representation to choose. Remember, it's not about which is better, but rather which is more suitable for your needs. Until next time, keep exploring.